Good morning. Good morning. All of you. எல்லாரும் தமிழ் தெரியுங்களா? Yes, sir. யாருக்கு தமிழ் தெரியாது? நடு தமிழ் பேசுறேன். This is a very special program organized by the Tamil Nadu State Department, and the person behind that, the motivator behind that is with us now, Dr. BISAG-N. I am very, very happy to welcome all of you on behalf of both IITs Madras Department and also on behalf of the Tamil Nadu State Council. It's a joint program. I'll say a little bit about this before, a little after, as soon as I introduce the other two members. I'm very thankful to Professor G. Shekhar, who is the current head of the Department of Chemistry. And he himself is a very distinguished organic chemist and has been my colleague for more than or close to a couple of decades, almost 20 years. And I am very, very happy that Professor Shekhar could find the time and also speak to you for a few minutes. And sitting with us next to me is Professor Sankararaman, and a national and an international organic chemist. He is currently Professor Emeritus like me. Retirement. He formally retired from the department 2 years ago, but we continue for another 4 to 5 years as we contributing to the department's teaching and research, and also for our own independent research activities, which the institute has facilitated some of us. I'm very happy to have Professor Sankararaman. He will also give you the first lecture. He will give 2 lectures, but he will start the program with a formal lecture when the program starts. So, about the department, Professor Shekhar will say many things to you. And I have kept myself as the lecturer in when there is a necessity to fill, and I think I will speak to you tomorrow morning about the topics of research of my own, and also the last lecture day after tomorrow. But most important, we have a purpose in bringing all of you here. At least in my understanding, the purpose is that every one of you has been selected, is among the best of the batch of students, the most motivated. I'm not saying the others are not very good, but you are the most motivated and you have shown interest in chemistry, try to learn and try to be a chemist, so to come to postgraduate level. You have been doing very well in the colleges. Therefore, it is time for all of us to find so many of you who would not have had the chance to join us after the JAM examination as our PG students. With colleges all around the state, we would like to bring you and tell you what many of our faculties are doing. Given the time limit of 3 days and logistics and various other reasons, and you are also now in your regular classes in your institute, so you have to take 3 days of leave. Given that logical constraint, it is important for all of us to tell you what is exciting in chemistry from our own perspective. But in this process, we also record these deliberations. Please ask questions, feel free to ask questions, and don't worry about whether questions are good questions or bad questions. There is no attachment to the questions, there is no adjective to the questions. Questions are questions, to ask them. Whether you know the answers or not, whether the faculty know the answers or not, will come through the deliberations. And the deliberations are important. And the recording of this session is also helpful for many of your colleagues and friends in the other institutions who didn't have the opportunity to attend this program. Logically also, and logistically, we cannot have more than 40-50 students in any program to have a face-to-face interaction, one-to-one interactions in classes. Therefore, we record this and we hopefully see that this is available to the rest of the student community who are interested in the programs in IIT, programs in IISc Bangalore, programs in the National Institutes of Technology for PhD, and we hope that all of you will somehow convince yourself that doing the next step of research in chemistry and becoming distinguished chemists in the future should be one of your goals. We hope that it will be. Okay? With these few words and the purpose for which you are here, in my mind, being told to you, I would now request Dr. Devasenapati, who is the program coordinator, to say a few words, and then I would request Professor Shekhar to introduce you to the department.
Good morning all, and Professor Mangal. When I first approached Professor I was just asking him about how to go about with a summer training program for 21 days. How we could do, what curriculum and all that. So immediately Professor said, let's do a 3-day program for government and government-aided colleges and see how it goes. Then based on that, we'll finalize the curriculum for the 21-day program, which will be held during the summer months. So that is how this advanced chemistry workshop came in. And so you are here for 3 days and try to make the best use of it. And there are several other students who had applied but couldn't get into this because of the number constraints. So கிடைத்த வாய்ப்பை நல்லபடியாக பயன்படுத்துங்க. இதுல இருந்து ஒரு 20 பேராவது ரிசர்ச்சுக்கு வருவீங்கன்னு நாங்க நம்புறோம். இல்ல சார், மினிமம் நான் சொல்றேன். சிலருக்கு வேற இது இருக்கும். எல்லாரும் வந்தா சந்தோஷம். 20-25 பேர் 50% வந்தாலே எங்களுக்கு அது ஒரு சக்சஸ் தான் இந்த ப்ரோக்ராமோடது. உங்களை மோட்டிவேட் பண்றது தான் எங்களுடைய இது. அதுக்கப்புறம் நீங்க அதை எப்படி எடுத்துட்டு போறீங்கன்றது உங்க கையில தான் இருக்கு. இதெல்லாம் கொடுப்பாங்க, இதெல்லாம் இருக்குன்ட்டு அதை நீங்க எப்படி எடுத்துட்டு போறீங்கன்றது இட்ஸ் லெஃப்ட் டு யூ. ஸோ மேக் பெஸ்ட் யூஸ் ஆஃப் இட். சயின்ஸ் சிட்டின்றது ஒரு கவர்மெண்ட் ஆஃப் தமிழ்நாடு ஆர்கனைசேஷன், ஹையர் எஜுகேஷன் கீழே. எங்களுடைய வேலை இந்த ஸ்டூடெண்ட்ஸ், ஹையர் எஜுகேஷன் ஸ்டூடெண்ட்ஸ், யூஜி பிஜி ஸ்டூடெண்ட்ஸுக்கு இந்த மாதிரி சயின்ஸ் ரிலேட்டட் ப்ரோக்ராம்ஸ் நடத்துறது தான். நாங்கள் சிட்டி ஸ்டூடெண்ட்ஸ் மட்டும்தான் இவ்வளோ நாள் கவர் பண்ணிட்டு இருந்தோம். ஏன்னா எங்களுக்கு அகாமடேஷன் ஃபெசிலிட்டிஸ் இல்லை சயின்ஸ் சிட்டியில். ஸோ வாட் வி யூஸ் டு டூ ஒன்லி ப்ரோக்ராம்ஸ் சென்னை பேஸ்ட் இன்ஸ்டிடியூஷன்ஸ். ஸோ முதல் தடவை சார் எங்களை அகாமடேஷன் கொடுத்து எல்லாம் இது பண்ணிக்கலாம், ஸோ ஸ்டேட் லெவலில் பண்ணலான்றது. திஸ் இஸ் த ஃபர்ஸ்ட் டைம் எங்களுக்கு ஸ்டேட் லெவலில் ஒரு இது பண்ணுறோம். அண்ட் ஐஐடி கூடயும் we had resource persons coming to Science City and delivering talks, but this is the first time that Science City is doing a program at Science City. Thanks to Prof. Mangal Sundar, and hope you have a wonderful time. Make best use of it. Thank you.
Thank you very much for your kind words. We will try to do what is relevant to the students. So not only through this program, but through this program, broadcast it to all the students who otherwise would want to be part. I will do our best. Professor Shekhar, please. Thanks.
Very good morning to all. First, I would like to thank Science City for coming forward to organize this advanced workshop for chemistry for 3 days. And from Department of Chemistry, I thank my colleague, Professor Mangala Sundar, for doing all the arrangements. I will talk about Professor Mangala Sundar. Also, on behalf of Department of Chemistry, IIT Madras, I welcome one of our resource person, our senior faculty member, Professor Sankararaman, and all of you to this workshop. When I came to know about this workshop from my colleague, Professor Mangala Sundar, I was very happy for 2 reasons. The first one is that IIT Madras now have a new program recently launched by our director, IIT Madras for all. Anevarkum IIT Madras. So the purpose of this program is that taking IIT generally in the village side or most of the places in the country, they think IIT means is something where we cannot enter. Okay, that's the opinion. People don't even think about JEE or don't even think to come inside IIT. So that is not the case. That's the purpose of the this particular program, and IIT is doing a lot to break the myth, so that people should feel free and they think IIT is also It's a good institute, but we can reach. So that's the purpose of the meeting. So early this month we had an open house, IIT Institute open house. The institute was opened for the public, and you will not believe 45 students, 1,000 students came to IIT, visited all the departments, and this is a record break. So so this program, I feel that it is falling in that direction, IIT for all. And second one, conducting advanced chemistry workshop at chemistry department, jointly organized by chemistry department and science city, is a right place. That's what I very seriously feel it, because our department is one of the best departments in the region, and of course one of the best department in the country. As per the QS ranking, the world ranking, we stand number 4 in the country. And if you see the facility wise, obviously our faculty members are, one of the best faculty members we have in the country, obviously. And research output wise also, our department is one of the best in the country. And if you see the research facility, where you are going to use both the ways, the lecture wise or hand-on experience going and visiting the instrument facility. Just in the last 2 years, our director, Professor Kamakoti, has allotted 45 crore rupees to our department to buy the instruments, high-end instruments. It's not for the whole IIT, only for our department, 45 crore rupees. And now, if you take NMR, so in the institute we have 6 NMR instruments. The department itself we have 2, which was upgraded very recently, and third one is getting installed now. We have 1 in the central facility, and we have 2 in safe. So within 100 meter radius, we have 6 number of NMR. The department itself we have 3 single crystal XRD, 2 HRMS, and so on and so forth. So I strongly feel that this is the right place to conduct this kind of workshop, so that the opportunity for you to see the instruments will be really very good. And our faculty members, I should not tell again and again, I don't think you will be able to find anything better than this in this region, at least, if not in the country, at least in this region. And to talk about the department, so we are having 32 faculty members, and we have 4 emeritus professors, 1 visiting professor, and 7 or 8 distinguished and adjunct professors in the department. And we have around 25 supporting staff, and we have 300 PhD students here. So we have presently 2 degree program offered by our department in IIT Madras. The first one is PhD program, started when IIT was started. So presently we have 300 PhD students, and again the institute is one of the largest department in the name of a PhD student. And we have, if you want to do PhD at IIT Madras, you should be either GATE qualified or NET qualified with fellow JRF. With LS, I think we don't shortlist. So if you are GATE qualified or if you are NET qualified with JRF, you can apply, or if you are Inspire Fellowship, if you are topper in all of you are topper in your college, am I right? If you are topper in the university, top few students, they can apply for Inspire Fellowship, and if you are getting it, that is equivalent to say JRF or UGC JRF, then you can apply to IIT Madras. Then your application will be shortlisted, and if you are shortlisted, you will be called for the interview. And if you are getting through, the success rate in the interview is very high, because the shortlisting takes care of other things. So once you clear the interview, you can join IIT Madras Chemistry Department, or for any department. This is the procedure. And we have 2-year MSc program. So if you want to join 2-year MSc program, your relatives or friends in your village, you can advise them, you can inform them that there's a 2-year program at IIT Madras. And if you want to join, you have to clear a national level exam, JAM we call it, and you have to apply to IIT. That's a procedure on the website. And if you are getting through based on your ranking, and you can come to our department. We have around 70 students per year So put together for both the year MSc students, we are having close to 145 students. And also our department has around 75 to 80 project staff and postdocs. So this is the strength. And also I am very happy to inform you that this year onwards, we are starting a new undergraduate program, BS. It's a 4-year BS program. We can continue the 5th year as a MS. So this is a new one. And entrance will be most probably by IGNOU aptitude test. That's what we are exploring, because now a lot of process we are going to do it. So the classes hopefully will start in the last week of July 2025. So we will be taking around 30 students, the first batch. So you can inform your people in the village or your friends, relatives, that if you are completing +2, if you are interested in joining IIT Madras for your undergraduate program, it's a 4-year BS program, extendable to 5th year MS program. So the entrance can just watch or look for our website, and hopefully this is the IGNOU aptitude test. So if you are clearing it, and you should be able to come to IIT Madras even after your +2. So this is the new program we are starting. So hope that hopefully it will become a flagship program for our department. So again, coming back to one of the organizers of the conference, Professor Mangalasundar, and I just know I told Dr. Dev Sanapati that Professor Mangalasundar is, I used to tell like that, with love, it's a Karnan of our department. So I have not seen anybody like that. Any problem you have, you go and ask him. He will, with a smiling face, he will give you a solution. And if you have any financial crisis, if you go and ask, sir, I need 3 lakhs or 5 lakhs for this kind of program to organize, he will say, hey Shekhar, 5 lakhs is enough for you. You may be going there to ask for 2 lakhs or 3 lakhs. So, but it's really amazing personality to have in our department, and this whole program is supported by him. I think they are not even charging any fees, accommodation, everything is provided. It's all just because of you people are from government college. So most of us are from government college, including myself. So please use this opportunity. We are going to stay in the campus for 3 days. It's a very, very rare and good opportunity. And we have the wonderful campus, one of the best campuses in the country, for sure. Is a nice, dense forest in the heart of Chennai city. Just you come inside, then you will see there's a different world altogether. We have nice, not only high quality research is going on, it's not only high quality teaching is going on, and also you have wonderful campus life here. We have a lot of deers here, monkeys, of course some snakes. Okay, you have to be just enjoy, explore the campus, and when you have free time, please feel free to visit chemistry department. Officially you will be going, am I right? There will be an arranged program, but other than that, whenever you have free time, just you walk into any research labs and you can introduce yourself saying that I am here in the 3 days workshop, I am interested in doing PhD, and I want to know about this organic synthesis lab, I want to know about atmospheric lab, or I want to know about battery technology, I want to know about main group chemistry, or whatever it is. We have around 35 labs open almost 24/7, and you will see always some PhD students will be working there. So this is opportunity, right? Directly you can visit the lab. Even if you want to meet any faculty members, you just go and meet the faculty members. If you have any query related to your overall about IIT programs or department or a particular research problem, say for example you are interested in total synthesis, or you are interested in organic synthesis or main group chemistry, NMR spectroscopy, you have a person there, okay, sitting there, you are in the campus, just go and meet him, and whatever queries you have, they will be happy to talk to you, they will be happy to explain you, and they will be happy to solve your or give the solution to your queries. And with all, as our organizers said, that if you are coming back to our campus as a student, if you are MSc student, so if you are coming as a PhD student, I think that will be the success of this particular workshop. I'm very sure that most of you will make it. So have a nice 3 days workshop, and it will be, I'm very sure it will be very beneficial for your professional growth. Thank you very much, and once again I welcome you all to our campus. Thank you.
So, as the last item, or as the first item of the next agenda, is that Professor Sankararaman will be giving you the initial lecture, or the lecture number 1. Later he will follow it up. And he's a very distinguished organic chemist, one with whom I have had many interactions. I'm a theoretician, but I find that there are problems that he brings it to me, and discussions make me think a lot about how one should interpret and think about theoretical chemistry and its applications in organic, basically reaction mechanisms and other areas. I have benefited from discussions. He started in 1995 when I came here. He was the seminar in charge for our employment, interviews that we did. That's the time I met him, and we have had a wonderful professional relationships until now. He's distinguished in the sense he has been a chairman of the selection for the project selection board, SERB, that is the Science Educational Research Board of the Government of India for project sanctions to faculty members in major institutions. He has headed that, and he's the fellow of the Indian Earth Science Academy, and also many other distinctions. And most important, academically, the book that he published also received a foreword from one of the best chemists in the world, theoreticians and symmetry expert, Professor Raoul Hoffman. And his book on the orbital interactions is a very well-known book. He has published in many major journals, and you will hear from the horse's mouth, as they say in English, organic chemistry, aromaticity, and reaction mechanisms, and physical organic chemistry from him. Therefore, without any further delay and without any further break, I would request Professor Sankararaman. So we'll formally begin the lecture, and from this point onwards, you put lecture 1, lecture 2. Okay? Thank you, and wish you all the best for 3 days.
Good morning, everyone. First of all, let me thank the organizers for giving me this wonderful opportunity. It's a very rare occasion that I talk to school students, actually. Although we have a summer program where the school students come and stay in the campus, and that is a separate program. This is a unique program, and I am very proud to be part of the program. Coming to the topic, how many of you heard the term aromaticity? Only one person has heard? All of you have heard the term aromaticity. So I cannot talk about aromaticity. Is that it? 200 years back, an important discovery was made in London by Michael J. Faraday that is relevant to the aromaticity topic. He distilled benzene in the pure form and characterized benzene as an organic substance. And since then, benzene has been in chemistry organic chemistry has changed its color because of benzene. Aromaticity, the term aroma comes from the fact that smell. Many organic compounds are pleasantly smelling, particularly esters, but not all of them are aromatic in nature. Aromatic compounds are having smell. For example, if we take trinitro tertiary butyl xylene, that is a synthetic musk. Synthetic musk is an aromatic compound, believe it or not. Aromaticity is a concept in chemistry. It explains the extraordinary thermodynamic stability of compounds. and the magnetic properties of the compounds also. It has a very strong theoretical background, strong experimental support. Benzene is a typical aromatic compound. Benzene itself is a starting material for making this class of compounds. For example, alkylation of benzene will give you ethyl benzene, cumene. Hydrogenation of benzene will give you cyclohexane. Nitration of benzene followed by reduction will give aniline. Chlorination of benzene will give chlorobenzene. So, I have given on the right hand side the use of these compounds which ultimately come into market, for example, polystyrenes, polycarbonates, epoxy resins, phenolic resins, nylon 66, nylon 6, all of them are derived from benzene as a starting material. So, if benzene were to not available to us, many of these industries will suffer because the raw material will not be available to them. Benzene is a classical aromatic compound, C6H6. It is isolated first by Faraday in 1825, 200 years back. So, we are actually celebrating 200 years of benzene. This is a sample. This is a benzene that Faraday distilled. It is available even today as an exhibit in the museum in London. He called it bicarbonate of hydrogen. That is a wrong name because it corresponds to a formula of CH2, C2H. That means C6H3 was the formula that he proposed. That is because in those days the equivalent weight of hydrogen was not known. So, erroneously they called it as bicarbonate of hydrogen. After many years, benzene structure was determined, and Kekule is the one who proposed the cyclic structure of benzene. It's a funny story that he had a dream of a snake catching its own tail, and that is how he came across the cyclic structure of benzene. However, he made a mistake of suggesting equilibrating structures. Structure 1 and 2 are actually in equilibrium according to Kekule. If they are in equilibrium, then the dibromo compound that you produce will be two types of dibromo compounds. The 1,2 dibromo compound has a single bond between the bromines, whereas this has a double bond between the bromines. So, this has to be distinctly different from this, but that is not the case. No individual existence of these two compounds is possible. So, later on the structure was corrected as a non-equilibrating structure, but a delocalized structure, resonance structure. So, the arrow has to be, even today some of the students make the mistake of drawing the wrong arrow for the resonance hybridization. Resonance hybridization should be illustrated with a double-headed arrow, not a double arrow like this. Hydrogenation of benzene gives you cyclohexane, and that is a important discovery that is made. Kekule proposed the cyclic structure of benzene in 1865, that is nearly 40 years after Michael Faraday isolated the benzene. Cyclic nature of benzene was finally determined by X-ray crystallography of hexamethyl benzene by Kathleen Lansdale. The crystal structure itself was determined in 1958. The former East Germany honored Kekule by releasing stamps on the occasion of 100 years of benzene formula. You can see here 100 Jahre formula, that is 100 years of benzene formula is celebrated by issuing a postage stamp by the Deutsche Bundespost. Benzene has several isomers. This is Landenberg isomer of benzene, in other words known as prismane. This has an independent existence and it's a fully saturated compound. Benzene is this one. This is a non-planar structure. This is a book-like structure, an open book-like structure. And the Claus benzene is this one, where you have crisscross bonding of the carbon-carbon bonds. Crystal structure of benzene was carried out at -3 degrees centigrade because at room temperature it is a liquid. You cannot determine the crystal structure of a liquid, and the solid is necessary, crystalline solid is necessary. Cruikshank was the one who determined the crystal structure of the benzene. This gives you the electron density map of benzene, which clearly tells you that benzene is a cyclic compound with 6-membered ring, symmetrical 6-membered ring. So it has a D6H symmetry in terms of the symmetry property of the benzene. However, the reactivity of benzene was very different from that of other unsaturated compounds. The ethylene, for example, is much more reactive towards proton or electrophile compared to benzene. The strong electrophiles are required often using catalyst, one can activate benzene ring. But the reaction of benzene never destroys the ring itself. It substitutes the hydrogen in a way such that the integrity of the cyclic nature of the benzene is preserved during the course of the reaction. This is because of the fact that you have a delocalization of electron. Temporarily it loses its aromaticity during substitution reaction. Sigma complex is formed and that is not an aromatic intermediate. So benzene itself is found to be stable towards reagents which are readily reacting with alkenes. This is because of the fact that benzene has extra stability arising out of aromaticity. We know that now, but in Faraday's time, benzene structure itself was not known. Hydrogenation of cyclohexene has an exothermicity of 28.6 kilocalories per mole. Cyclohexatriene, a hypothetical molecule, will have 3 times the hydrogenation energy of the cyclohexene. So that would be around 85.6 kilocalories per mole. Benzene has only 49.8 kilocalories per mole. The difference of 36 kilocalories per mole is the resonance energy of benzene because of the delocalization of benzene pi electrons. Here is a Huckel molecular orbital theory method of determining the energy levels of various orbitals of benzene. Ethylene has 2 orbitals, 2 pi electrons, so 2 orbitals are there in ethylene. This is a bonding electrons, pi electrons of benzene, and this is a anti-bonding level which is empty. In case of benzene, hexatriene, for example, you have 6 pi electrons, but it is not a conjugated system. It is just like a ethylene system. So 6 pi electrons are arranged one above the other in this manner, and the alpha is a Coulombic integral and beta is a delocalization integral. Energy of pi electrons in ethylene is 2 alpha plus 2 beta because of 2 electrons are involved in this. So multiplied by 2, 2 alpha, 2 beta will come. Here it is with 6 alpha, 6 beta in the case of hexatriene unit. Huckel molecular orbital calculations invoking delocalization will give you 6 alpha, 6.8 beta. 0.8 beta is higher in energy in the case of delocalized structure. Benzene structure is, electronic structure is given here. The total energy of the pi electrons is given as 6 alpha, 8 beta. The delocalization energy therefore is 2 beta, which is excess energy. In the case of the hexatriene, which is a hypothetical molecule, the difference between benzene and hexatriene is this is a olefinic bond, not a completely delocalized system. So, it is a non-delocalized structure of the alternative double bond, single bond is given here. Pictorially, the pi orbitals are represented in this manner. This is a sigma framework. Sigma framework of benzene, 6 carbons and 6 hydrogens are there and they are sigma bonded. This is a sigma bond. Whereas the p orbital of benzene is given here. The p orbitals are perpendicular to the plane of the benzene ring and the p orbitals are also delocalized in terms of complete delocalization of the electrons, which gives a sandwich kind of a arrangement here. This is like a donut shaped electron density above and below of the planar benzene ring. So, the criteria for aromaticity according to Hückel, this criteria has been modified now quite a bit. It should be a planar compound, it should be a cyclic compound, benzene like compound, uninterrupted cyclic cloud of pi electron, that is a delocalization of pi electron. Odd number of pairs should be there, 1, 3, 5 like that, 2 electron, 6 electron, 10 electron. In other words, 4n plus 2 electrons or pi electrons should be there for it to be aromatic. This is known as Hückel's 4n plus 2 rule, and all the 3 conditions should be met by the compound to be aromatic. For a planar compound to be aromatic, it should have uninterrupted cyclic pi cloud containing 4n plus 2 pi electrons. This is the definition of a aromaticity in terms of anti-aromaticity is just the opposite of aromaticity. Instead of 4n plus 2 pi electron, if you have 4n electrons, then it becomes anti-aromatic. This explains the extraordinary thermodynamic instability of the magnetic property and instability of the compounds. High reactivity pattern is observed in this cyclic compound having a planar structure containing 4n pi electrons. Butadiene is an example of a 4n electron system where n is equal to 2. So, if you consider the 3 molecules that are mentioned here, namely cyclobutadiene, benzene, cyclooctatetraene, this is anti-aromatic in nature, this is aromatic in nature, whereas this is non-aromatic in nature. What is meant by non-aromatic? It is like a olefinic compound, this is what it means. Why is it like a olefinic compound? The structure of cyclooctatetraene is not planar structure, it is a tub shaped structure. This is in one plane and this is above the plane of the other 2 plane. So, there are 2 planes one can define to define the structure of cyclooctatetraene. Benzene is aromatic, cyclic planar uninterrupted where n is equal to 1, where 4n plus 2 is 6. Cyclobutadiene is anti-aromatic because of the fact cyclooctatetraene is non-aromatic in nature, is like olefinic kind of a compound is what is given here. Cyclooctatetraene can have different forms, different conformers for example. One can consider a completely delocalized structure of cyclooctatetraene. This is planar delocalized structure. This has a D8D symmetry present in this system. This is a C8 symmetry in terms of an axis of symmetry passing through the center of the ring. Here, the planar localized system, in other words, the double bonds are not delocalized here. So, it will be a C4 axis of symmetry with the appropriate plane of symmetry corresponding to D4-8 symmetry in terms of the. This is a D2D symmetry. This is non-planar structure of benzene, tub-shaped structure of benzene, sorry not benzene, cyclooctatetraene. And if you consider this to be the reference point of zero energy, this is 10.6 kilocalories higher in energy, and this is 14.7 kilocalories per mole higher in energy compared to the tub-shaped system. So, here is an example that delocalization does not necessarily lead to stabilization of electrons, stabilization of the compound that we are dealing with. Delocalization can destabilize the compound. From this example, for example, from 0 energy to 14.7 kilocalories per mole, relatively speaking, this is less stable compared to this one. A generalized MO picture of aromaticity and anti-aromaticity is given here. In the case of aromatic compound, you will have a closed shell system in the sense that the orbitals will be completely filled up in terms of electron filling in the, whereas in the case of anti-aromatic system, it is an open shell system. This has a 8 electron system. So, 2 of the electrons are not paired here. It is almost like a diradical state is what is given here. This is a 8 electron system, 10 electron system. The 10 electron system n is equal to 2. So, 10 electron system is an aromatic system. So, aromatic systems will have a closed shell system, whereas non-aromatic or anti-aromatic systems will have open shell system. Open shell system means it has unpaired pair of electrons. Unpaired electrons will be there. Unpaired electrons means the radical nature is coming into picture. So, they will react like radicals. Benzene, aromatic compound having occupied molecular orbital completely filled with no unpaired electron. So, this is a bonding level of benzene. There are 6 pi electrons, so 6 electrons are filled in according to the Aufbau principle. Then non-bonded level is given by the dashed line here, and empty molecular orbitals are there which are non-bonded anti-bonding molecular orbitals. So, this is bonding level, this is anti-bonding level, the in between non-bonded level is given by the dashed line here. The MO picture of benzene is given here. This is a completely donut shaped electron density distribution in the ground state, which is psi 1, pi 1 of benzene. Pi 2 of benzene should have one node. Node is a point where the electron density is going to be 0. So, the electron density in these points are 0, close to 0. Similarly, the electron density in these points are close to 0. So, this has one node present in the system. This also has one node present in the system. This is a nodal point. And here the nodal point goes through the atoms, carbon atoms. Here the nodal point goes through the center of the carbon-carbon bond. That is the difference between the two systems. Then you have two nodes. Two nodes are perpendicular planes of this type or this type, for example. Here again it goes through these atoms. Here it goes through the center of the bond. Then threefold nodal points are there here. These 3 planes are nodal planes in this benzene structure. In the case of cyclobutadiene, it does not have a completed shell of electrons. This has 4 pi electrons. 4 pi electron, 2 pi electron comes in the ground state molecular orbital of first molecular orbital. Then the second and third molecular orbital will have 1 each. This is because of the Hund's rule of maximum multiplicity. You cannot put both electrons in the same orbital. They have to have different address, so they have to have different orbital occupancy. So, this corresponds to a diradical kind of a state in the cyclobutadiene case. It is easy to draw the diagram of molecular orbital pictures of these aromatic in general anilines by means of a diagram called the Frost diagram. Have you heard about the Frost diagram? Pardon me? Frost diagram is an idea which gives the relative energies of molecular orbitals in a closed ring polyene system. The polyene system is put inside the circle such that one of the atom is at the bottom of the circle. Then you draw the hexagon for benzene. So, these points where the atom meets the circle corresponds to a molecular orbital of this. So, this corresponds to the point here. These 2 points are given here. The center point is a non-bonded level, which is this one. Then comes the antibonding level, 3 antibonding levels, 3 antibonding levels. To fill up the electrons, of course, you have to go through the Aufbau principle. 2 electrons are filled here. Totally 6 electrons are there in benzene. So, 2 electrons here and 2 electrons here. So, it is a closed shell system in terms of the reactivity pattern of the benzene. Whereas, in the case of cyclobutadiene, it is an open shell system. These 2 electrons are not paired here. They occupy the bonding level. As a result of that, they act as a diradical species. Because of the nature of the molecular orbital filling, the butadiene, cyclobutadiene synthesis itself is very difficult. It can be synthesized from dibromo cyclobutene using zinc. Debromination reaction will give you the cyclobutadiene. This has to be trapped above 35 Kelvin. It's very cold conditions. Above 35 Kelvin, it dimerizes to a dimer. So, it undergoes a 2+2 cycloaddition reaction to give a dimer like this. Or in the presence of a trapping agent like cyclopentadiene, it undergoes Diels-Alder reaction to give this compound here. Cyclobutadiene is unstable. It can be isolated and controlled condition such as argon matrix. Argon matrix crystal structure has been done for this. This is a 1.56, 1.434. The double bond and single bond character is shown here, which tells you that it is not a completely delocalized system. If it is a delocalized system, all the 4 bonds will be equal in length. That is not the case in this case. Heterocyclic compounds can be aromatic in nature. For example, pyrrole, thiophene, furan, all these compounds are aromatic in nature. 4 pi electrons and a lone pair of electron is given here. The lone pair of electron in the case of pyrrole, furan and thiophene is pointing in this direction, allowing the delocalization of electron in this particular case. There are 2 electrons of lone pair and 4 electrons of the pi electron. So, totally 6 pi electrons are there in this case. So, these are aromatic in nature. The case of pyridine, the lone pair of electron and the nitrogen is not involved in the delocalization of electron because of the fact that nitrogen is already trivalent and it has a pair of electron which is on the plane of the benzene ring, not perpendicular to the plane of the benzene 6-membered ring. So, as a result of that, this is not a delocalized electron, this is a lone pair of electron, and that is why pyridine is a strong base in terms of availability of this lone pair of electron for protonation. If we consider these compounds where nitrogen is at the center of the molecule, this also has a lone pair of electron, but it is not a delocalized lone pair. The pi electron is in this particular fashion delocalized, whereas the central 2 pi electrons are not delocalized in the sense. So, it is 4 plus 4 plus 4, 12 electron system. This is non-aromatic in nature, this is anti-aromatic in nature, whereas this is 4 plus 4, 8 plus 2, 10 electron system, it is an aromatic system. You understand? What I am saying is there is a difference between the orientation of pi electrons in this fashion, which is parallel to the other pi electrons, or in this fashion, which is perpendicular to the pi electrons here. If it is perpendicular to the pi electron, it is not going to be delocalized. It has to be parallel to the pi electrons for delocalization to take place. Annulenes are cyclic hydrocarbons having alternating double bonds and single bond. Benzene itself is an annuline, it is 6 annuline. It's 8 annuline is a cyclooctatetraene, 4 annuline is cyclobutadiene, 10 annuline is this particular compound, so on. There is no criterion that it has to be planar compound. Annulenes are not necessarily planar, especially when it comes to higher annulenes like 10 annuline, 14 annuline, and so on. This is a 10 annuline system, 10 pi electrons are there. This cannot be planar because of the fact that two hydrogens, if it is planar, the two hydrogens will poke into itself. These two hydrogens will interact with itself, sterically hinder the approach of the other hydrogen from becoming planar. So, this is a non-planar compound. In order to make it planar, instead of hydrogen, you attach it with a CH2 group here. This is a 12 annuline, it is an anti-aromatic system, this can be planar. This is a 14 annuline system, aromatic system. Sixteen annuline system again is a non-aromatic system. 18 annuline system is aromatic system. These higher annulines are going to be fluxional in nature, in the sense that the hydrogens which are interior of this hydrogen pointing in the interior of the ring. There are 6 hydrogens pointing at the interior of the ring, 12 hydrogens pointing on the exterior of the ring. So, this is a aromatic system or not will depend upon whether it is a planar compound or not. (20 annuline). As I mentioned in the 10 annuline case, the two hydrogens are pointing interior of the ring, so they cannot form a planar structure because of the steric interaction between the two hydrogens. So, they tied up the two hydrogens using a methylene group. So, remove the two hydrogen, put a CH2 group and connect the CH2 group onto both the carbon. You will get 10 methanoaniline in this particular case. This is more or less a planar molecule. So, it is a diamagnetic ring current effect is shown here. This is a bond, this is a completely delocalized system, 10 electron system, this particular case. This is the structure of the compound that I am dealing with the methylene bridge in the 14 annuline systems are not very stable. They can undergo conformational change in this manner. However, this can be locked in the conformation by means of 2 carbon units. This is a locked system where the conformational flexibility is not going to happen this particular instance. So, as a result of that, this can be a planar 14 electron system, which is a aromatic system. So, 14 pi electron system is aromatic system in the nature. How do we show that it is aromatic? NMR spectroscopy is useful for identifying aromatic compounds. NMR spectroscopy deals with nuclear spin. So, proton NMR spectroscopy means you are dealing with the nuclear spin of proton in the spectrum. And the nuclear spin of proton produces its own magnetic field, and in the presence of external magnetic field, it will have 2 orientations, aligning with the orientation, opposing the orientation. So, in that case, the pi electrons are delocalized and they produce their own ring current effect, what is known as ring current effect. So, the ring current effect is going to be shown by means of delocalization of the pi electron and circulation of the electron around the ring, that produces its own magnetic field such that whatever proton you put in the center of the aromatic ring will get highly shielded, and whatever the hydrogens that are in the periphery of the aromatic ring will get highly de-shielded. So, such a shielding and de-shielding zones are called anisotropic effect of the aromatic system, and very useful NMR data is very useful for deciding the. Similarly, here it is an open system. This is a closed system. It is still 18 aniline, 18 electrons are there here. This is also 18 aniline in nature, core and plus 2 electron system. So, this is aromatic system, both are aromatic system. 12 anilines are anti-aromatic in nature. If you add 2 more electrons, it becomes 14 aniline, right? So, 14 aniline becomes aromatic in nature. For example, this is not a stable compound above minus 50 degree. It undergoes reaction and it decomposes itself. Whereas, if you reduce the compound with lithium, lithium is a good reducing agent. It is alkali metal element. So, it can donate 2 electrons to the anti-aromatic compound and make it into an aromatic compound. So, these 2 electrons will go into the 2 pi which are not fully occupied. Remember, anti-aromatic systems will have the open shell system. Open shell system will have unpaired electrons in this case. So, the open shell system becomes a closed shell system by addition of electron, which is a reducing agent, is lithium as a reducing agent. Then it becomes aromatic in nature. Similarly, 16 electron system becomes 18 electron system. That is also aromatic in nature. These are some examples of aromatic systems, anti-aromatic system. Here, although you have acetylene, 4 pi electrons are there, only 2 pi electrons are in the same plane as the 2 pi electrons of this nature here. So, each of the acetylene, although it has 4 pi electron, only 2 pi electrons will count for each of the acetylene towards the aromaticity. The other pi electron is perpendicular to the plane of the benzene, the ring here. So, as a result of that, that electron is not going to be counted for delocalization. Do you see that? It is like, for example, you have the acetylene has 2 planes, perpendicular planes, and in this particular plane, the orbital will be pointing above and below the plane. Here it will be towards me and towards you, orbitals will be orienting. So, only these orbitals are going to be counted for the aromaticity and not the aromatic. Here is an interesting molecule, it is called keculene. People wanted to know whether it is an aromatic compound or an anti-aromatic compound, whether it is an anulinic compound or whether it is a aromatic compound or a simple aniline compound without any aromaticity, non-aromatic in nature. Synthesis was made through elaborate synthetic strategy, and it can exist in 2 forms. It can either exist in the aniline form. In the aniline form, you see that conjugated double bond, single bond is alternating here. This is 18 aniline. Outside also there is a alternated double bond, single bond aniline is there. This is a 30 aniline. This is the largest aniline that is known probably. So, 30 aniline and 18 aniline are both aromatic in nature. but the difference is that it will have a ring current effect which will shield the hydrogens here very much. NMR spectrum of the compound should show highly shielded hydrogens and highly de-shielded hydrogen in the ratio of 6:30. But what the NMR showed was a structure corresponding to this one, where you have a double bond and triple bond not alternating in this particular structure. Sextet is formed in these rings. So, the benzenoid structure is what is prevalent in the compound, and these hydrogens come in the normal aromatic region. They do not have any shielding or de-shielding because of the ring current effect. They come in the normal aromatic region of the NMR spectroscopy. So, it shows that the structure of the compound is more like this one rather than an aniline type of a structure. So, it is an aromatic compound, not an anti-aromatic compound of any kind. Ionic compounds can be aromatic in nature. 2 electron system, 4n plus 2, where n is equal to 0, 2 electron system is an aromatic system. Cyclopropyl cation is an aromatic system. Cyclopropyl cation is an aromatic system. This can be prepared by ionizing the corresponding chloro derivative. Cyclopropenyl chloride can be ionized to give the cyclopropenyl cation. This crystal structure of this compound is known. This is a planar ring, 3-membered ring, and these are propeller shaped molecule. And this is ferrocene. Ferrocene is an aromatic compound because of the fact cyclopentadienyl anion is a aromatic ligand. Cycloheptide triennyl cation is also aromatic in nature because of the fact it is a 4n plus 2 electron system, delocalized system. Cyclooctatetraene dianion is also aromatic in nature. I should stop here because the other teacher is waiting. So, I hope I was able to give you some flavor of the phenomenon called aromaticity. I hope it is useful to you in your studies. Thank you very much for